Hello students, coming to the next video of next third video of flexural strength of PSC beams for the flange sections. So in the last video we learned about flexural strength of PSC beams for rectangular sections as well as for T section whose neutral axis was within the flange. Now in this video we'll see the flange sections where the neutral axis lies within the web. A beam section may have flanges at one end or both, which may be precast or cast at site. For example, we have T sections, I section, we have box section, double T sections as well as double box sections. So these are the examples, these are the figures. Now if the neutral axis of the flanged section lies within the flange of the compression section, that is the XU neutral axis depth XU is less than the depth of the flange DF, then the section is designed as a rectangular section as designed in earlier video 7. Now if the neutral axis of the flange section lies beyond the flange of the compression section, that is the neutral axis depth XU is greater than the depth of the flange DF, that is it lies in the web, then the section is designed as flanged section whose analysis is entirely different than the rectangular section. This is the figure for the neutral axis lies within the web. Suppose consider a I section whose width is B and effective depth is D. Now this section whose neutral axis lies in the web is analyzed for two different sections, one for the web section and another for the flange section. This is for the web section and this is for the flange section. Addition of these two will give the complete analysis for the flanged section. Now this is the stress block for web portion, where you have CUW as the total compressive force for the web and TUW total tensile force for the web. The lever arm is D minus 0.42 XU is the lever arm for this. Now if you consider the stress block for the flange section, this is the stress block for the flange section, which is a rectangular stress block. CUF is the total compressive force for the flange and TUF is the total tensile force for the flange. The lever arm is D minus 0.5 DF, where DF is the depth of the flange. So CU is 0.36 FCK BXU and CUW is 0.36 FCK BXU and TUW is FPU into APW. CUF is 0.45 FCK B minus BW into DF. TUF is FPU into APF. Suppose APS is the total area of pre-stressing steel, which includes area of steel in flange and area of steel in web. So APF is the area of pre-stressing steel for flange and APW is the area of pre-stressing steel for web. So therefore the APS is equal to APF plus APW. So total is APS. FCK is the cube strength of the concrete, FPU is the ultimate tensile strength or tensile strength developed in the tendon at failure stage of the beam. FP is the characteristic tensile strength of the pre-stressing tendon. D is the effective depth of the section. So therefore APS is total area of pre-stressing steel is APF plus APW, pre-stressing steel for flange and pre-stressing steel for web. Now consider considering the stress block of flange portion to determine APF now. So we will determine first APF. So considering the flange portion, that is considering this figure, so I need to determine APF now. So I will take the equation for sigma fx equals to 0. So therefore TUF is equal to CEF, total tensile force is equal to total compressive force for the flange. So total tensile force for the flange is APF into FPU, and total tensile force for compressive force for flange is 0.45 FCK B minus BW into DF. So for that, with that, the equation for APF will give you 0.45 Ck B minus Bw into Df divided by FPU is the equation for area of prestressing steel for flange. Now considering stress block for both flange and web, so the moment of resistance for the entire section is the sum of moment due to moment due to this couple plus moment due to this couple. So moment due to couple for web portion plus moment due to couple for the flange portion. So if you consider that, it is TUW into the lever arm, TUW into the lever arm D minus 0.42 XU, TUF into the lever arm D minus 0.5 DF. Either you can take TUW or CUW, and TUF or CUF. So TUW the web portion is TUW into the lever arm plus flange portion is TUF into the lever arm. So substituting TUW is APW FPU, and TUF is APF into FPU. Now we know what is the equation for APF. So equation for APF is 0.545 CKB minus BW into DF by FPU. Substituting that here, so APW FPU D minus 0.42 XU as it is for the web, plus for the flanges APF is this bracket term into FPU into D minus 0.5 DF. So FPU get cancels. So the moment of resistance for the flange section final equation is APW into FPU into D minus 0.42 XU plus 0.45 FCK B minus BW into D minus 0.0 DF. So this first equation is for this term is for the web portion, and this term is for the flanged portion. So this is the final equation for moment of resistance for the flanged section. Now when you know, after knowing the area of steel in the flange, now you can determine area of steel in the web. So to area of steel in the web is the total area APS minus the APF. So APW is equal to APS minus APF. Now in case of flanged section, the reinforcement index APFP divided by BDFCK. So this, when the neutral axis lies in the web, so instead of APS it is APW FP divided by, instead of B you should consider as BW D into FCK. So that means for neutral axis in the web, APS is replaced by APW and B is replaced by BW. So this is for the flanged sections. Now considering a first problem here. So the problem is we have a T section whose size flange is 1200 by 150. The depth and the width and the depth of the rib is given as 300 and 1500. Area for HTS wire is given, which is located at effective depth. So directly the effective depth is mentioned here. The characteristic strength and of concrete and steel are mentioned. Now you should determine the flexure strength of the section. Now we don't know whether the neutral axis lies within the flange or the web. So first of all, draw the section. So the T section flange is 1200 by 150 and width of web rib is 300 and depth is 1500. This is the rib. Effective depth is this is effective depth is 1600 mm. Now very first what we need to do is, first of all, we don't know whether the neutral axis lies within the flange or not. First you assume neutral axis lies within the flange. Calculate the reinforcement index W is equal to APF APFP divided by BDFCK. Substituting the values, we will get the reinforcement index W as 0.095. Now with this reinforcement index, now determine XU by D as well as the value of FPU by 0.87 FP. Now instead of calculating FPU by 0.87 FP, so we will first only calculate XU by D and ascertain whether the neutral axis is within the flange or the web. So referring IS code IS 13443 1980. So determine XU by D. XU by D is 0.217. So 0.217. So therefore, if you don't get the direct value, you can interpolate and get the value. So XU is 0.217 into D, that is 1600. So therefore XU is 347 mm is the XU value. Now this the flange is, how much is the flange depth? The flange depth is 150. 150 is the flange depth. So therefore 347 is greater than the depth of the flange DF. How much it is? It is 150 mm. So therefore the neutral axis lies beyond the flange. So therefore assumption is wrong. Neutral axis lies beyond the flange, that is in the web. Now when it is beyond the flange, now determine the area of prestressing steel for flange first. Area of prestressing steel for flange APF. So APF equation is 0.45 FCK into B minus BW into DF by FPU. DF by FP. So the value is 0.45, FCK is 40, B minus BW, B is 1200 minus 300 into depth of the flange is 150 divided by FP 1600. So APF you will get it as 1518 mm square. This is the value of APF. Now with this APF, so calculate area of steel for web. Area of steel for web. So AP W is equal to total APS minus APF. So the total area of steel is 4700 minus for the web 1518. So APW is 3182 mm square. So this is the value for area of steel for the web. Now when you determine the area of steel for the web, now determine the reinforcement index. Now reinforcement index W, now the neutral axis is in the web, therefore the W is APWFP divided by BW D into FCK. So that means APS is replaced by APW and B is replaced by BW. So substituting the values, 3182 into 1600 divided by BW is 300 into 1600 effective depth into FCK 40. So the reinforcement index is 0.265. Now for this reinforcement index 0.265, now this is a case of whether we need to refer table number 11 or 12. So is it pre-tension or post-tension? So this is a problem of a pre-tension. So therefore referring table number 11, refer table 11 of IS 1343 1980 for W is equal to 0.265 FPU by 0.87 FP is 1.0 and XU by D is 0.56. So now with this calculate FPU. So FPU is 1 into 0.87 into 1600. So FPU is 1392 Newton per mm square. This is FPU, ultimate strength of steel. Now XU by D, XU value will be 0.56 into effective depth 1600. You will get XU as 896 mm. This is the value of XU. Now knowing FPU and XU, the moment of resistance for the flanged section is mu is equal to equation APW FPU into D minus 0.42 XU plus 0.45 FCK B minus BW into DF into D minus 0.5 DF. This is the equation for moment of resistance for the flange section. Substituting the values, 3182 into 1392 D minus 0.42 XU, D is 1600 1600 minus 0.42 into 896 plus 0.45 FCK 40 into bracket B minus BW, 1200 minus 300 into DF is depth of the flange is 150 into D minus DF 1600 minus 0.5 DF is again 150. So calculating this, we'll get the value as 19125 into 10 to the power of 6 Newton mm. So therefore moment of resistance of the given section is 9125 kilonewton meter. So this is the final moment of resistance of the given section. Now we'll take the next problem, second problem, the last problem. The second problem is it is a symmetrical I section 300 by 750 overall depth with flanges and web of 100 thick. The beam is post tension here. The beam is post tension by cable of 48 wires of 5 dia. So there are 48 wires of 5 diameters. Eccentricity is mentioned here. The 28 days cube strength is mentioned. Now let us draw the section. It is symmetrical I section. Three hundred overall depth is mentioned as 750 is overall depth. The eccentricity is mentioned as 250. So therefore the effective depth is 750 divided by 2 plus this 250. So this effective depth is 625 Now similarly this problem you can solve it by yourself. I'll give you the answer this for this. So assume neutral axis within the flange, calculate the area of steel is APS is you have 48 wires. So 48 wires of 5 pi by 4 into 5 square. So calculate this APS. Then for post tension, now you have to refer table 11 or table 12. Just see it is post tension, but let us see whether it is bounded or unbounded. So here they have mentioned that assuming grouting of tendon to be 100% effective. So that means grouting is done here 100%. So that means there is effective bond between the tendon and the concrete. So therefore it is again post tension bounded. So it is table number 11 only. So refer table 11 and calculate XU by D. First of all calculate this reinforcement index for this. So calculate reinforcement index. W is equal to APSFP divided by BDFCK. So you will get it as somewhere around 942 mm and 0.47. Sorry, 0.23. We'll get it as 0.213. So with this reinforcement index, so the XU by D you calculate from the table, it will be 0.433. So and if you calculate XU, it will be less than, so it will be greater than, the depth of the flange. Therefore the neutral axis lies in web. Assumption will be wrong. Therefore then you calculate AP of area of steel for the flange, you calculate. So and that is 211.76. Calculate area of steel for the web, you will get 730. Now calculate new reinforcement index W for the flange, so which is APW FP divided by BW DFCK. Calculate this. So with that reinforcement index, calculate from the table FPU by 0.87, FP you will get it as 0.75, and XU by D you will get it as 0.653. So with all calculate FPU from this and XU from this. So calculating these two, then substituting in the moment equation MU, you will get it as moment of resistance as 574 kilonewton meter. So try this problem and get this answer. So this is how the moment of resistance for the flange section can be done. Now supposing if you have any other problem of suppose double T section, if you have, this completes the problem, second problem. Now suppose if you have double T section like this. So in this double T section, so this will be the width of the flange, complete entire width of the flange. When you assume neutral axis within the flange, you take this width of the flange. Now when you get neutral axis beyond the flange, then this will be BW1, this is BW2, width of the web. So the final width of the web BW is sum of these two, BW1 plus BW2. So that is the change in case of a double T section. Suppose if it is a box section, single box section of like this, when you assume neutral axis within the flange here, so take this as the width of the flange, and when you get a neutral axis beyond the flange, this is BW1, this is BW2, and if you get neutral axis in the web, so the total width of the web is BW1 plus BW2, that is a change. And suppose if you have double T, a double box section, suppose we have something like this, then so this is the double box section, this is BW1, this is BW2, this is BW3. So this will be the total width of the flange. When you get the neutral axis beyond the flange, so then the total width of the web is BW1 plus BW2 plus BW3. So this is how you can take the width of the flange as this, and the remaining will be similar calculations. So this completes the problems on flexural strength of PSC beam for neutral axis beyond the flange. So this video ends the total complete module on flexural analysis of PSC beam. Thank you.